Once you have those two files, the JXL and the folder containing all your data, then we can open up Trimble Business Center, which you'll see represented by this icon, and import that data and go through the data processing workflow. Go ahead and open it here. As I progress through this video, I still have a good cough that comes on every once in a while, so I'll try to pause the video when that happens so don't blow out your speakers, but don't think your computer's glitching if the video jumps around a little bit. It's just me. So to start things off here, minimize that for a second. You should come to this starting page. This is Trimble Business Center 5.20, and it is installed in those four of the computers in the back of the GSL near the survey storage room. All three of the computers in the first row have the software, and then the first computer in the back row has it, and that's it for now. So you're going to have to, you and your team are going to have to share those computers with the others in the other sections. So we'll start by doing new project. We're going to select US survey foot. That's what we did for our units when we were out there laser scanning. And then we're going to immediately go to File, Save As for the project. We'll call it Trophy Point Example. Hit Save. One other preliminary admin step is we're going to go to File. Oops, wrong one. Looking for let's go here. There's a little gear up here. I'm going to select that, and we're going to go to Coordinate System, and we're going to say Change. I'm going to say Coordinate System here. You want to get United States /ITRF to NAD83, and then you see here that it's allowing you to use the NAD83 2011 EPIC. That's what we want. And we'll go down and find New York East 3101, hit next, leave the geoid model as set by default, hit OK. So now your grid that's laid out here is actually northing and easting coordinates associated with that New York East state plane coordinate system. So next step is we want to bring our data into the environment, so we'll go to Import, and we need to go find the directory in which you have your information. So in the initial part of this video, we need to track down where we saved the data. After you brought it onto the hard drive, I recommend saving it on your local computer that you're using in the GSL there. And so I have mine in the Documents folder here in the SX10 example. And if I point this Browse for Folder utility to that, then it will show what's in there, and you should see the JXML file that you exported, and then that automatically pulls the data from the other folder that's it was stored with it. So to import, here, I would let this go ahead and run through, and you'll see why. This is it just taking the color digital imagery that was taken before the scan started, and it's projecting the color onto the point cloud. So it can serve as another way to visualize the points, and it shouldn't take too long. Okay, so here it's loaded. We're looking at this top-down plan view. You can zoom in with the mouse wheel. If you right button click, then you can pan it around. The Left button click is just going to select things like I just did there, and then I can click outside of that or hit the escape key and it'll do that. But in this plan view mode, we can't rotate the view around and see it in 3D. So to do that, we make sure we're on the home tab here, click 3D view. It will generate a new tab, and then we can zoom in, and then if you push down on the mouse wheel, you get to rotate in 3D and explore your data here for the first time. Now you'll notice some unique patterns to the data, a lot of black space, which means you don't have any points there. This is a lot more black space than we would expect to see in normal operating conditions because of the snow. So thinking back to the days of remote sensing, for those that have been exposed to that class, what we have going on here is a specular reflection. So because of the texture of the snow, when you get this smooth surface that it can generate, especially when it freezes into the slippery ice, that laser beam comes in at a high incident angle and bounces off the surface and never returns to the instrument, and you get no data point returns. You'll see all these localized areas where you get points surrounded by black space. That is likely a lot of the footprints and things where you have indentations and part of the wall of the footprint is at an advantageous incident angle and is sending data or sending light back scattered to the scanner. But in other places you're not getting that. A couple other things to point out here as we're just looking at the data. It places the scanner location there, so you see where that is relative to the rest of the information. You get to see the points you used, okay, to capture or to perform your resection. So you can do a double check on that and make sure it's coming in as you expect it to. Here we'll see that's part of the building that was captured in this scan. Pretty neat. So to play with the colors, right now it's, if I go to the point clouds tab, I'm under color coded intensity. Well, it's not viewing that right now, so we got to update it. Right now it should view true color. That's what it means when you're looking at the color from the camera. If I go to grayscale intensity, that's taking the intensity of the laser point return and just giving it a white to black color ramp. You can also change that to color-coded intensity, which provides more colors than the black and white scheme. Okay. Okay. This example data set that I brought in is only one scan. So there's no real registration to do. In most of the cases for all of you, I hope that there are at least 2 scans so that you can perform this step. But what we're going to do is the scans should come in together and be very close to being aligned because of the resection work you did. But the next step is to do a refinement of that co-registration, so it looks at the 2 point clouds where there's overlap and fits them together even better. And so to do that step, before we do anything else, we'll just click on a portion of the point cloud, and we should see it fill in all with this different color. And then we'll go to register scans under the point clouds tab. Now it'll probably default to this plain based. You're not going to do that one. You're going to go to the refinement tab, and if you have more than one scan, you should see them listed here. Go ahead and pick the first scan you did to be fixed. So check that box and then uncheck or leave unchecked the remaining scans. And what that means is it's going to take that first scan you did, it's going to lock that down in 3D space. And then the other additional scans will be fit to that point cloud where the algorithm can find geometry that matches up. So we'll translate it and rotate the rigid point cloud in 3D space to match better with that. And it works fairly well, and it's fairly automated. So you'll select which point cloud you want fixed, and then you'll hit refine overall registration. It will take a variable amount of time. You'll see a progress bar down here, and when it's done, just run it once. You can hit close. Okay. Now that we have our point clouds as well registered as possible, now we are going to perform another automated process that is going to attempt to extract the ground surface or differentiate the ground surface points from any objects that are on top of it. So buildings, vegetation. It does a pretty good job. It's never perfect, but we'll go through and review the results a bit here after we do it. So to do this, you're going to remain in the point clouds tab. You're going to select, so it turns that sepia tone again, and then you're going to go extract ground. While this is running, I want to remind you to take screenshots. You can just use the snipping tool for the purposes of this lab, but take some screenshots of your exploration of the point cloud, different steps. They'll serve as great visuals for your presentation and your write-up summary. Just to kind of anything you find interesting in the data, and especially when we get to being able to review these ground extraction results, areas where you see it's not working well. Okay, so it looks like it finished here. Sometimes it takes a little bit longer than others, and different data sets take different amounts of time, but just be patient once it's running. But the progress bar reached 100%. It kind of stalled there for a while, but it eventually wrapped it up. So if we zoom in here, we'll see that some of the data is darker than others, and what you're seeing there is the ground separated from objects like the tree trunks and vegetation and buildings, and then the representations of people here. Who's this goofy guy? Oh, that might be me. Okay, so to then separate the data and just visualize the ground points, we have to go into this point cloud regions line here, and we'll see now we have default and ground. Default is everything that it's saying is not ground. So if we want to turn that off, we click it, left click it, and then right click and say toggle visibility, and it will turn that off. Okay, so now if we take an overview shot of this, that is all the points that it thinks are ground, and it's removed as much as it could confidently say is not ground. As we zoom in here, you'll see it, even these rocks that were around here got removed, but it's not perfect. So you have these little kind of fins sticking up. And if you were doing very detailed work for this site, there would be some manual cleaning that would have to take place. How is that done? It's not too bad to do. It just gets tedious when you have to do a lot of it. So I'll show you how to do a part of this rock here that for whatever reason the algorithm got confused about. The biggest thing when dealing with point cloud data is when you want to start selecting it in this 3D world, but you're looking at it with this 2D screen and using a 2D interface device, is that if I draw a window, which I'm going to do here by selecting this button down here, and I start clicking, and to get this started you have to hold down the left button, and then you can let go and then start clicking when it's to complete it, then double click to finish. It's going to select that one region. So what I just did there, I created a window, but it selects everything above, below, and in that polygon. So if there was data back behind it here, it would get selected. So sometimes you have to get pretty tricky cutting cross sections in the data with the cutting plane and things to just select the data you care about. Here we have it there. And then if I take that selection there and I say add to region. It opens up a tool here. It's still selected. I tell it I want to take that selected region and add it to the default layer. And then I hit add. And by default, it really means non-ground features. And you can see it disappeared because I had that default layer turned off already. So that's an example of how you could manually go through and improve this. For the purposes of this assignment, we're not going to get into the nitty-gritty there of deleting everything that is non-ground that was retained in here. And we'll smooth some of that out with the way in which we make a surface here. Okay. A couple other things to notice in the data here. So here's one of the paths, the asphalt paths. You have this topography that's rising up here, and that provides better incident angles with the scanner back here. But then those horizontal surfaces have very high incident angles, so you're getting specular reflections on them and therefore no data points. If you want to play with the point size, because it's pretty small here, you can hit up here and select medium. That makes them a little bigger. You could say large, makes them even larger. You can put back on true color, which is never perfect, but it gives you an idea of what you're looking at. Okay, so that is simplifying the point cloud down to ground points. There's obviously a lot more data there, and it could be used. It just depends on what your goal is. So if we turn this back on and then turn off ground, you get just this data set. And if this was a civil engineering project where you are very interested in this building and the dimensions of the windows and the texture of the stone and all that, then you would be focusing most of your time on the structural aspects of this building as opposed to the ground surface. Okay, the next thing we're going to do with our extracted ground points here is we're going to resample them. Big thing with terrestrial LiDAR is you get variable density of points, and especially when you add the specular reflections that are taking place outside of these footprint regions and things. And so we're going to try to smooth that out a little bit, and one of the ways you can do that is by resampling. And so we'll select the data set. We're going to say sample by region, and we'll leave all this stuff the same. I'm going to choose 1/10 of a foot. You could experiment with this. You could try 2/10 of a foot, but we'll go ahead and do that. We'll hit store. It's going to create a new region here that tells you the sampling interval you used. And then I'm going to toggle this one off. Make sure we're looking at what we want here. Let's try to get everything turned off. Okay, and turn just this one back on. This is what we're going to work with from now on. So if I zoom in here, you'll see that it's gone through, and where points were closer than 1/10 of a foot, it deleted them and just retains the others, so you get a little bit more of a uniform sampling in regions that you did capture. And that will help smooth out our surface a little bit. Okay. So it is at this point, depending on where you go, so for the teams that are going to go the GIS route, ArcGIS Pro is preferred because of the type of data you're bringing in, or being large LiDAR data. You are going to take this point cloud and export it as a LAS file and bring it into GIS and make your digital elevation model there and contour it. For those going the CAD route, we're going to go ahead and make a specifically Civil 3D or Autodesk CAD software. We're going to we're going to create a surface here and then export it as a land XML file. That 3D surface could then be brought into CAD, and then you can figure out how to turn that into a contour plan. And there's quite a few examples of that being done on the internet and YouTube and all that. So if I were to then take my resampled point cloud and bring it over to ArcGIS right now, I would have it selected, I would go to Home, and I'd go to Export. I would select the point cloud button here, and then I hit Last Explorer. Okay, it says I have one selected, this point cloud. Make sure you're using your resampled one. It has a name here based on my project, and it's going to save that to my Documents directory where the Trimble Business Center project is being stored. I'm going to have it not sample the points any further. I'm going to have it export units in US survey feet, and then I'm going to have the scaling be in grid. Okay, that's just tied to that New York State plane system. And then I hit export. Okay, now that was saved as a .las file. That is compatible with ArcGIS Pro. You can bring that in. There's a tool called Las to Raster. You can then make an elevation raster from this where you choose your own cell or pixel resolution. And I'm going to leave that to you to figure out on your own. But there are references out there. Close that up. Okay, so now to make a surface in TBC here, we got to go over to the Surfaces tab. We're going to select it, and we're going to say Create Surface. It's going to say, what do you want to call it? I'm going to rename it Topo. Okay. And we're going to go ahead and hit OK. It's going to compute on this data set and really triangulate in between the points, or interpolate in between them. So then when it's done, we can zoom in. You can see where the points align with the triangulated surface that was created. Okay. We're then going to turn the point cloud part off so we can just focus on the surface. Okay. And you can see in areas, it works out pretty well in areas that were captured well with the instrument. And then you get this interpolation across the path there, and then more grass slope. In and around the region where the scanner was, we saw in the original point cloud that it had its issues, a lot of dropouts or those specular reflections, and then a lot of uneven, weird features associated with footprints in the snow. And so that doesn't really result in the greatest looking surface, but a lot of that is coming from the snowy conditions, which if this was really being done to capture the topography of this region, then the work would have to be postponed, but we don't necessarily have that luxury given the end of the semester is fastly approaching. So here we have a surface of created from the data that we were able to capture. You'll notice some areas where some large triangles were generated. And I'm going to try to trim that down a little bit because this just represents areas that we don't have much confidence in. You know, we just have some points along here and over here, and you have these triangles that could be hundreds of feet long, and that's not ideal. So we want to be a little bit more deliberate about where we're surface modeling. So if I go to the surfaces line here and expand that, go to Topo. If I click on that, it automatically selects the surface that we created, and you can see how the triangular mesh was developed. So it's variable density where you had a lot of points and returns. You're getting these nice small triangles. But in areas where you don't have data, it's interpolating long distances. So we can click here and say Properties. And we're going to focus on maximum edge length. So default to 500 feet. That's a little too large for what we're doing. So I'm going to change that to 20 feet. Hit Enter. And it's going to recompute the surface. and it's going to throw out all those triangles that are really large. And so you can see we miss out on some of this area here, but that's okay. You can experiment with different size. If you just try different numbers, it will keep redoing it. But now we have a surface where, you know, we're focusing more on the areas that we do have data. Okay. So it's at this point, and I recommend the GIS groups do this too. It's helpful to see kind of how your data is being represented as a surface in TBC. But you can also calculate contours in here, but this is the surface that I would recommend for the CAD groups to take this surface and export it to CAD and do the contour calculations in CAD and develop your topo map / topo plan in there. But to do contours just to see how they look really quick, you can use the quick contour tool. Here I'm going to say let's do 1 foot contours. We will say index contour frequency, so we'll say every 5. So that means every 5th foot should be an index contour. So you could change the color of that, make it more bold, and have the contours in between it be a lighter line weight. But that's getting into the details. And then we'll hit OK. It's going to compute those, and there we have some contours. You'd have to tweak some things more so in the create contour tool, not the quick one, to get the labels to work out and everything. But like I said before, I recommend doing the contours in ArcGIS or CAD and figuring out how to make the labels work in there. But this is what we're after eventually, is having a nice topo map of the region you captured with your laser scanner. So go to home here. We can look at the top view. We could even turn off the surface. We just have our contours. Okay. So real quick, to export your surface, if you're going to bring it into your Autodesk CAD software, we'll need to have it selected, and then you'll go to the export tools, and here you're going to click on construction and do land XML.